So our next talk is by Erich Grädel on logic and bisimulation for guarded terms. Teams, sorry.
Okay. Yeah. Thank you very much. What I would like to do in my talk is to bring together two threads of research in logic, which have not been present in this workshop so far. One is logic of dependence and independence, which are based on team semantics, and I will briefly explain what this is. And the second, perhaps more well-known, is guarded logics and bisimulation. And what we aim at is to bring this notion of guardedness into this setting of team semantics. So we study notions of guarded teams and bisimulations for guarded teams. And our main objective are characterization theorems in the style of Van Bentham theorems that relate on one side logics on guarded teams, on the other side invariants under these appropriate notions of bisimulations in this setting, and at the same time gives a translation between the setting of team semantics to classical Tarskian semantics, which will be inside existential second-order logic in this case. So first, let me recall what guarded logics are. Right? They have been introduced in the 90s by Erich, Van Bentham, and Nemeti. And the idea is to restrict familiar logic, such as first-order logic and fixed-point logic, in such a way that we always talk, in all subformulae, only about tuples or assignments that are close together in the sense that they coexist in some atomic facts. For instance, an edge or a tuple in a larger relation. So we call an assignment giving values to variables x1 to k in the structure A as guarded if there is some atomic fact that covers all these values of the assignment. And from this, we can get guarded fragments of familiar logics by restricting quantification either by a semantic definition or a syntactic one, so to ensure that all the free variables of the formula are guarded, right? Because guardedness is, of course, definable by a formula that is rather easy to write down, or we can explicitly give the atomic formula that defines the guard. Right? And so we relativize quantification syntactically to guarded assignments. And an important point is that these guarded logics preserve almost all the convenient properties that modal logics have and lift them to a much more powerful setting. And I would even say that guardedness in some way explains why modal logics are so good. And there are a number of results. These have been obtained all of them between 10 and 15 years ago. So the guarded fragment of first-order logic sits between modal logic and first-order logic, and if you do the same thing for fixed-point logic, you get something that sits between the modal mu calculus and LFP. And the good properties of these guarded fragments can be summarized as follows. The satisfiability problems for this guarded logic is decidable. The guarded fragment of first-order law has a finite model property. I think this is even true for, you proved it, right, that it also is true for guarded fixed-point logic.
It doesn't have the finite model property, but has decidable, you can decide it.
Oh, okay, yeah. Although, of course, that's not a finite model property. It's very easy to, sorry. Yeah. Okay, but perhaps even more important fact is the tree model property, that every satisfiable formula has a model of small tree widths. So essentially up to interpretation a tree, and this paves the way to automata theoretic methods for working with these formulae. And also the model checking problem is much simpler than for first-order logic in general, because the associated evaluation games have small size due to guardedness. So you have to, in a quantification, you have to go out to all elements, but just those that preserve the guardedness. Right? And more recently, there are it's been a renewed interest. There are new extensions to more powerful variants of guarded logics. So loosely guarded and clique guarded are old ideas, but more recently this fragment of guarded negation has been introduced by Barani, Ségouffin, and Tenkate, for instance, right? So, but the general message is that these are well-behaved, tame fragments of logic that have good model theoretic and algorithmic properties. Now, an important tool to study such guarded logic is a variant of bisimulation. So it's now in classical bisimulation, you have a game moving around single vertices of a graph. Now you move around guarded assignments in a similar way. I won't define it precisely. This is not really important here. But we have a notion of guarded bisimulation saying that a particular assignment in one structure is guarded by similar to another assignment in another structure, right? So tuples can have not fixed lengths. This may change during such a process. In particular, can also consider the empty tuple and say that the two structures are bisimilar. But it's the same idea. And with this idea, we get van Bentham-style characterization theorems, in the sense saying that the guarded fragment of first-order logic is precisely the fragment of first-order logic that is invariant under bisimulation, and same thing for the fixed-point fragment. So guarded fixed-point logic is the fragment of second-order logic, first of all, where we restrict quantifications to guarded relations and then takes a bisimulation invariant fragment. So this is an analog of the van Bentham characterization theorem for modal logic, and this is an analog of the Janin-Walukiewicz theorem for the modal mu calculus. Question is, can we get similar result in team semantics? But then we should first know what team semantics is. Now, team semantics has been introduced by Wilfried Hodges, and well, the idea is that a formula is not, as in Tarski semantics, evaluate against a single assignment giving values to the variables, but against a set of such assignments. Right? And a set of assignments with a strain domain of variables is called a team, for actually rather bad reasons, but this is how it is. The original motivation was to provide a model theoretic rather than a game theoretic semantics for a particular logic of dependence. It's the independence-friendly logic, IF. Right?
So is the structure, are your structures finite or not necessarily?
Not necessarily finite. So structures can be anything.
You can have infinite sets of teams.
You can have infinite teams. You can get infinite teams. Yeah. So, and the semantics is a formula true in a structure in a given assignment for a given team, right? And a motivation for this is that when you look at dependent statements, like this variable is dependent from that, or these two variables are independent, this doesn't really make sense if you just consider a single assignment. You need large amounts of data to make sense of this, and this large amount of data can be, for instance, a table or a team, right? And this team semantics is a very important innovation, in my opinion, going far beyond the original application. And is really the basis for the modern logics of dependence and independence that go back to Jouko Väänänen. And the idea is that...
Sorry to slow you down, but what does it mean that formula is true under...
We can come to that. Well, at least a bit, right? I will not really define it. But just hint a bit. So, first of all, we start at the atomic level, right? If you know these classical ways of making sense of dependence and independence, like Henkin quantifiers of IF logics, then dependence or independence are, in a sense, special quantifiers or annotations of quantifiers. Well, said no, this is an atomic statement. Right? So consider the various notions of dependence as an atomic statement on a team. Right? And there are many of them. These are the four that are the most important ones, and for this talk, inclusion and exclusion are the most important ones. So dependence just would say the variables in Y are functionally dependent on the variables X in the given team. So any two assignments that coincide on X will also coincide on Y.
And it's written as equality. It looks like dependence is written as equality. Yes.
Yes.
Yeah. Okay.
Yeah. This was notion, as notation was chosen by Yoko. So, I mean, database theorists will recognize these things. These are variants of database dependencies that have been studied a long time, but not, say, as an atomic statement on which you would build a logic, right? So, it has been studied for different purposes. So, inclusion would say every value that occurs for X in the team also occurs as a value for Y. Exclusion is dual, saying the values that X may take and Y may take are disjoint, and independence is a bit more complicated. I will not go into it. Right? So the idea then is to combine such atoms with a logical connectives and quantifier to obtain full-fledged logics for reasoning about dependence and independence. And these logics require team semantics.
Can I ask you a question? Because you're defining a lot of things that I don't know yet. So to keep track, can you give a word about intuitively what dependent and independent means, why they're like dependence and independence? And
but dependence just is a very natural thing. It says that if you consider a table, right? The columns are the values that you have for one variable, the rows are the particular assignments. Now dependence means whenever in two assignments coincide in the value for X, then they must also coincide in the value for Y, which means there is a function giving you the values for Y from the values for X.
Good.
So functional dependence.
That is exactly functional dependency. Okay, so tell me about independence.
Independence says that the values occur together in all possible combinations. So since if you know the team, and I tell you what the value for X is for a particular assignment, you have nothing whatsoever about the value of Y. All values are still possible.
If I may, there used to be called multi-value dependencies if you open databases.
Okay.
Yeah.
Same thing.
Yeah. It's on the atomic level, it's the same thing, precisely.
Yeah, only at the
Yeah. Yeah. Mm-hmm. Yeah.
multi-value dependencies.
Yeah. So now if you add connectives and quantifiers, you get logics, like dependence logic, independence logic, inclusion logic, and so on. You get a wide variety of logic, and they all require team semantics. So the question is, what precisely does it mean that the formula holds in a structure for a given team? But I will not explain you in this talk, right? Go to Yoko Vanen's talk next week if you're still here, or to Fokyon's talk in the logic colloquium.
Okay, but by now we have some idea.
Yeah, and in fact I give you some more basic idea. And so an important observation is that if you just have first order logic but didn't add any dependence atoms, then this doesn't give something that is really significantly new. It just has a flatness property, which means that the formula is true for a team if it is true for all individual assignments in the team. Of course, this immediately breaks down when you add these dependence atoms. Right? And in the presence of non-flat dependencies, this gives second-order features to first-order syntax, in a sense, right? And the most interesting case is, in fact, disjunction, because disjunction splits the team, right? If you say, even here, right, if you say either phi or psi is true in the team X, you actually split the set of assignments into those that satisfy psi and those that satisfy phi. So this already introduces a second order feature, and quantifiers do as well. And the consequence, for instance, is that extremely simple formula can express complicated properties. 3-sat can be expressed by just a disjunction of 3 dependence atoms, 2 of which are the same. And with an inclusion atom, you can express ill-foundedness, that is the existence of an infinite descending chain, by a very, very simple formula. Right? So unexpected things appear. But to understand these unexpected things better, we can use a translation to Tarski semantics. Right? So we can, a formula in a logic with team semantics can be translated into an existential second order sentence that takes a team as an additional relation. Right? A team can be represented by a table that is a relation. So a formula with team semantics is translated into a sentence in Tarski semantics. And this sentence will be in existential second-order logic. So we can say, well, to understand the expressive power of a logic with team semantics, we have to identify the right fragment of sigma 1, 1 to which it corresponds in that sense. And, okay. So, and the results that are known say, well, if you just have exclusions or dependence, then this coincides with a fragment of sigma 1, 1 that is downwards closed, in the sense that the predicate for the team appears only negatively, which also means if a form is true for a team, then it is also true for all its subteams. If you add either inclusion and exclusion both, or if you add independence, then you get the full power of sigma 1, 1. So in particular on finite structures, you can express all NP properties of teams. And something very interesting appears if you just add inclusion logic, just add inclusion statements. Then, as Galliani and Hella proved, what you get is a fragment of least fixed point logic that uses only greatest fixed point and uses them only positively. But by Neil Immermann's result, we know that on finite structures, this is the full least fixed point logic. So on ordered finite structures, in particular, inclusion logic captures polynomial time, and it is, captures at least LFP on finite structures without order. But for infinite structure, you can't capture full LFP. I mean, full LFP is no longer in sigma 1, even it lives in the delta 1, 2 fragment. Right? And this extends when you add counting. Right? So we also get a characterization of fixed point logic with counting in this sense. So we want to bring this to teams. You'll see I have very little time. So the idea is to have also a guarded notion of team, and we just say all assignments in it are guarded. And then we now want to define a fragment of a guarded fragment of first-order logic for teams. We can either restrict the definition semantically so that all operators just talk only about guarded teams, or we can do it syntactically in the same way as one did in the classical setting, restrict quantification, relativized quantification by a formula that says everything is guarded. Right? So it's no problem to define a guarded fragment of first-order logic in teams. But the notion of bisimulation becomes delicate. There are actually two notions of bisimulation. So we can say that two teams, x, y, are bisimilar if they contain the same guarded bisimulation types. So when you have an assignment S in one team, then you must have a bisimilar assignment in the other team, and vice versa. But there is another possibility. You can say, well, we now look at this team as an additional relation and expand the structure accordingly and look whether these expanded structures are bisimilar. And this is, of course, stronger. It's a more restrictive notion. So when you're bisimilar in the strong sense, you're bisimilar in the weak sense. So if you are invariant under the weak sense, you're invariant under the strong sense. And the converse is not true. And in fact, one thing that witnesses this are inclusions and exclusions. They are invariant in the strong sense, but not in the weak one. And we can see this in this way. So we have here two structures. And when you take the assignment AB in one and the assignment A prime B prime, then these are bisimilar. You can do precisely the same things in two structures when you move these edges around. And also, the other pair of red edges, BC and B double prime C prime, are bisimilar. Hence, when we take the teams that combine this, then they are bisimilar in the weak sense because they contain the same bisimulation type. But of course, they are not bisimilar in the strong sense. You can go from a red edge to another red edge, and you can't do here, right? But when you notice that the exclusion atom saying sources and targets are disjoint, this is true in B, but is not true in A. So it's not invariant under the strong notion of, under the weak notion of bisimilarity, right? They are weakly bisimilar, but one satisfies the exclusion atom and the other one does not. And an identical argument shows this for inclusion as well. But on the other side, if we work in these expanded structures, so we can use this predicate for the team to guard our assignments, then we can easily define inclusion and exclusion, so they are invariant under this other notion of bisimilarity. But an interesting thing is that with this junction, this is no longer compatible. So although the individual exclusion atoms are invariant under strong bisimulation, the disjunction is not, and this can you see by classical method of finite model theory. If you take cycles, then each edge in a cycle is bisimilar to each other edge, right? But to split the cycle so that you cover the entire one in an inclusion respecting matter is only possible if the cycle has even lengths, right? So with a disjunction, you could separate cycles of even lengths from cycles of odd lengths, and thus break bisimilarity. Okay, now characterization theorems, what we actually want, right? So here is a characterization theorem, right? It relates many things with each other. So what is green are always logics in classical Tarski semantics, and what is blue are logics in team semantics. So what the characterization theorem says is that in team semantic, the fragment of first order logic that is invariant under guarded bisimulation is equivalent to the guarded fragment defining either syntactically or semantically. This is not important. But it also corresponds to those sentences of existential second order logic that you can write in this form. So just saying every assignment in X satisfies phi, where the predicate for the team does no longer occur in X, so just the flatness property expressed, such that this formula is in the guarded fragment. Or you take it to be an arbitrary formula and you take only the bisimulation invariant part. So we have, in a sense, many characterization theorems put into one, giving all the same formalism. Right? Now notice that these all describe properties of teams that are guarded horizontally, in the meaning that every individual assignment is guarded. But they are in first order logic, so it's downwards closed. Right? And there is also a stronger idea where you do not consider the properties defined in that way, but we start from what is definable in first order logic on the Tarski side. Right? So you look what is definable in first order logic with an additional predicate for team, but without this restriction how it occurs, can it occur in an arbitrary way, but it has to be invariant under guarded bisimulation. So of course you don't have downwards closure anymore, you can use this predicate X anyway. So to get a corresponding thing on the other side, you have to something to break this downwards closure, and what we have to add is classical negation. Right? Previously we had negation only on the atomic level. Now you have classical negation that you can really negate on the entire level of the team, but then you get a similar characterization theory. And I should say the proofs very much rely, I had it on the previous slide but I didn't tell you, on the basically methods that have been refined and developed by Martin Otto to bring down, to say that you can reason basically with bounded quantifier rank to prove such results. Now, it is tempting to assume that you can add a further thing that's just take as a guarded fragment with the additional predicate for X in Tarski semantic, but this does not work, but this is only invariant in the under strong bisimulation and not under weak bisimulation. So the question arises, of course, are there also characterization theorems for this stronger notion of bisimulation? And it turns out that on the first order level, this doesn't bring anything different. But this is not a true fact in general. And it relies crucially on the fact that, that first-order logic can only express flat properties, in the sense that something holds for a team if it holds for every individual assignment in the team. And if you don't have this, then the notions are different. And in fact, this is very interesting when we look at it on the level of fixed-point logic, because this is just guarded fixed-point logic in the sense used in the classical setting. And there is a characterization theorem that is known for that, right? We have a characterization theorem for guarded fixed-point logic under bisimulation, and when we understand the predicate as a team, we're just in the classical setting, right? So now we know that fixed-point logic is closely related to inclusion logic. So can we get a similar characterization theorem here? And well, in a sense, we have it to some extent, right? It is not really completed. In the sense we know that what is the invariant part of inclusion logic is contained in guarded fixed-point logic with a precise characterization, but we don't really know yet whether we have here an equivalence. So as an outlook, of course, this notion of guarded teams is just one way how one can define guarded teams. What we did, we guarded the teams horizontally. Every assignment has to be is a tuple that lives close together. We could also look at the columns. So look at the set of all values for one particular variable and say that that set has to be guarded, covered in some way. It is perhaps not as natural anymore to just guard it by the atomic facts of the structure. So we can look any system that would guard this, let's say a given guarding hypergraph that would cover this. And this also has natural motivation. So if you understand a column as a set of values that you observe in a particular measurement, for instance, right? It may make sense that these values are in a sense close together and only then make sense. And if they don't, then there must be some serious error with your measurement, or this value should be eliminated or whatever, right? So there are certainly also motivation to consider vertical notions of guardedness and define appropriate logics for that. So this is not really difficult. One can define such vertically guarded team semantics or vertically guarded first-order logic, but we do not yet really understand the expressive power of these. It very much depends on how you guard. There are extreme cases when you guard almost nothing, only singletons, or where everything is guarded, and then you get, not surprisingly, not something new, then this will collapse to classical cases. But there are intermediate cases where the power of these guards makes the complexity very high. We can get almost to full first-order logic. But at this point, this is more or less just an outlook, right? So we have a relatively good understanding what happens when you look at the horizontally guarded setting, and the vertically guarded setting is more an idea and a promise. But that's it.
So we could take one or two questions.
Would there be some automated theorem proving involving these that would be, say, applicable to database theory?
I don't know.
Can you express some
I mean, already, so database theory has considered implications between various forms of dependencies on the atomic level quite extensively in the 1980s. So, Janas and folk know a lot about this. And I think even there, a number of problems are in fact undecidable, right? So, of course, I mean, with the theme semantic, I mean, things become not easier as they become a priori more complicated, right? You reason in a more complicated setting, and the notions of dependence or independence are not so simple notions, right? They can cause you lots of headaches, and so I wouldn't expect that something in this direction is close, right?
So I was going to ask a similar question. Not having thought about these teams. I mean, it's odd, so it takes me a while to understand it. And partly I want to, if you could share a little more intuition of when it's really nice to have a team in when you want it. And the other is, because these come so straight from database dependencies, maybe there's a place for it in database theory where the nice notions can be easier to say that way. And maybe there'd be the small piece that would be actually very more elegantly expressible in database theory. Can you see what I'm saying?
Okay, I mean, let's say the motivation for this really, okay, logics of dependence and independence have been studied for a long time, but they haven't really come to the mainstream of logic, I would really say, right? So hope, of course, a strong proponent of this logic with team semantics has been Jouko van Annenen, and his goal was really to set up, say, a family of logics for reasoning of dependence and independence as they arise in many different sciences. So dependence and independence are really concepts that arise everywhere in science, and
in like statistics, that kind of independence.
In statistics, even in economy, and so it's not just a notion that is a notion of mathematics. It's a notion that appears in physics, in many sciences, and I think one of his main goals was really to build more bridges to other sciences and have a system for reasoning about dependencies and independencies that would go across sciences. Now, I'm not sure how far this goes and how promising this is, but that is one of the goals, right? Let's say my motivation is, other than I find these logics very interesting and nicely defined, that really the methods that we have in finite model theory and descriptive complexity and so on can bring something to understand the power of these logics and what the properties really are, and also what the algorithmic possibilities. A priori you are in a setting of NP of sigma 1,1, and it's completely unclear what are the fragments for which you can actually do something, right? But I think the methods that we have can offer here something, right? I'm not so sure about the connections to databases, because dependencies are of course important in databases, but is it so important for databases to have, say, all these logical operators on top of them to reason inside databases? This I don't really see. On the other side, I mean, Folkjohn has a very interesting connection to constraint satisfaction problems of say, a particular variant of dependence logic. So I think there are really interesting connections.
There is another aspect, if I remember talking to Jouko, that there are these partially ordered quantifiers which are not very amenable to use in logic, and he was by using this approach you can make the logic more modular of this. Now, can you also, but the question I wanted to ask is, in database we also have embedded say implicational dependencies. Can they also be used as that?
I think embedded multi-value dependencies are conditional independence atoms. It's it's more or less the same.
So there is a kind of mystery why set solvers work. So there is something in the typical case which works. So I wonder whether guarded fragments can explain at least a portion of it.
I don't think that guarded. I mean, let's say subsolvers work for typical instances. Guardedness is a way to make it work in every case, right? To really identify a fragment that. So, in a sense, I think the approach to guardedness is a completely orthogonal approach to.
In light of Fokien says this is propositional. What has it to do with this?
No, no.
So set was so successful. So in the places where first-order provers used to be used, people would take.
That's modular theory.
People would convert everything to set and run well.
I mean, a priori, set solvers can apply to any NP-complete problem, so they could be applied in this setting as well. Right. Of course, one could. Let's say I see no immediate connection. Of course, one could try to use SAT solvers to deal with formulas in dependence or independence logic.
Properties are natural. They were captured by this. So maybe there are more natural stuff or typical stuff captured.
Maybe, I don't know.
Thanks for a nice talk.